right, ladies and gentlemen, welcome. Welcome to a very important lesson. And I just got to say congratulations to Robyn. I watched her play Ada in badminton today, and my goodness, it was a massacre. All right, it's okay though. Ada, you just got to practice, okay? Actually, anyone in class, you want to challenge me in badminton, I will take you anytime. We'll play badminton in the gym, and tell you what, you will never beat me. It's just one of those things. Even though I'm a super old man, I know it's embarrassing for you to lose against an ancient guy like me. But you know, that's life. Join the club, okay? That's how it is, okay? That's my life. And even in like 100 more years from now, I'll still beat you in badminton, okay? So, but yeah, Robyn, great job today. Ada, work on it, okay? Just, you know, hand-eye coordination, that's all it is. All right, so let's take a look at a topic that is familiar to you that we covered a little bit, I think, when we did the space unit, but not in this kind of detail. So we'll get to that in a moment. But before we talk about that, today we were yesterday, okay, you were looking at this on Friday. So yesterday we talked about the speed of sound. Well, there's something that goes with that I forgot to mention it's not in the homework, but it is in today's homework. It's this thing called Mach number. Okay, Mach number, not match, Mach, okay? That's how it's pronounced. So the Mach number of an object is defined as the speed that the object is traveling. So you might have an airplane or a bullet or any object that's moving, okay, can be described in terms of its Mach number. And then you divide the speed of that object by the speed of sound, okay? And what you're doing is you're comparing the speed of a moving object to the speed of sound. That's what Mach number is all about. And what I did was I did an example for you here. So let's say the temperature of the air is 0. There's only one reason I would give you the temperature of the air, and that's so you can find the speed of sound. So we go ahead, find the speed of sound using the formula. At 0 degrees, easy enough, the speed of sound at 0, 332 meters per second. Now, let's say you're on a jet, and that jet is traveling at 390 meters per second. Which is actually amazingly fast, by the way, okay? So that's an incredibly fast velocity, and it is greater than the speed of sound, right, at 0 degrees Celsius. So the Mach number of this object would therefore be the speed of the object, 390, divided by the speed of sound. And you get this number, 1.17. Notice there are no units. It's not Mach number doesn't have a meter per second or anything. It's just a number. It means you're traveling at 1.17 times the speed of sound. You get it? So we're comparing your speed to the speed of sound, writing it as a ratio compared to the speed of sound. So if you have Mach 2, you're traveling twice the speed of sound. Mach 1, you're traveling exactly the same speed of sound. Mach 0.5, half the speed of sound. And that's how Mach number works. I do another example for you here. The Concorde jet could famously fly at Mach 2.4, okay? What is the speed of that object? Well, the speed of that object, if we use your brilliant math skills, let's not use a triangle, okay? Can you solve this equation for the speed of the object? And basically you multiply the Mach number by the speed of sound, right? So you're going to bring that up to the other side by multiplying both sides by the speed of sound. This is the equation you will get. So the speed of the object is the speed of sound times the Mach number. So speed of sound will go with 0 degrees Celsius still, so it's 332. Multiply it by the Mach number, and you'll find that that object is traveling at 796.8 meters per second. And that is an amazing 2,900, whoops, I kind of strike through it, 2,916.3, okay, kilometers per hour. That's pretty fast, okay? And that will take you, that Concorde jet could take you from New York to Paris in about an hour, okay, which is a pretty fast ride. All right, so that's how Mach number works. You'll see that in the homework, very easy, no problem, okay? Now, let's look at everybody's favorite, the Doppler effect. Now, I'm going to play a sound for you. And it might sound a little muffled. It's coming through the earphone that I have with me right now. So you tell me what you think this is. All right, so what do you think? Is it a police car? No, it's not a police car. Strike one, okay? Ambulance. Wrong again. Okay, let's go, guys. Get with the program here. It's not an ambulance. There's only one emergency vehicle left, really, when you think about this. So what's left? Well, if you guessed fire truck, you guessed right. Okay, it only took you 3 tries, but you guessed right. Okay. Now, can you tell the moment where the fire truck passes the person who's recording the fire truck? Okay, the person's just standing on the sidewalk recording the fire truck going by. Listen carefully. Can you hear the moment he passes him? Okay, again. Right there. So what happens is there's a noticeable shift in the pitch of the siren at the moment that he passes the person, the observer, we'll call him, okay? The person observing the sound. So what's happening is there's a shift, a noticeable shift from a higher frequency to a lower frequency, and then it stays lower the whole time he's driving away. It never shifts back, okay? This phenomenon is called the Doppler effect, and it happens with light, it happens with water waves, it happens with all kinds of waves. And in fact, it's a very useful thing. We can use the Doppler shift to measure the speed of an object, like the speed of a baseball being thrown, the speed of a hockey puck being shot, the speed of a car driving down the street. These devices we use to measure the speed of a moving object use the Doppler effect in order to do it. So without further delay, let's look in very great detail at how the Doppler effect works. Now, we looked at this in the space unit when we did Redshift, okay, Redshift and Blueshift for galaxies, okay, and how we knew the universe was expanding, and it's because most galaxies are redshifted, which means they're moving away from us. Anyway, let's look at that now and understand how that works. Well, let's say I have I'm going to put a little X here. Let's say I'm dipping my finger in the water. Well, when I dip my finger in the water, it's going to create waves that travel out in all directions that look like these circular ripples that you are seeing here, okay? Those are arrows indicating waves traveling out in all directions. And if you don't like my drawing, let's take a look at an animation, okay? And I'm going to change the perspective. All right, so you understand what you're looking at here is you're looking at a point source of waves right there in the center, and the ripples are traveling out in all directions from the source, which is the black dot at the center that's bobbing up and down, let's say in the water. That's it. Now, this is what the water waves would actually look like if they were real water waves. So here you get the waves traveling out. Oops, my arrows look terrible today. That's all right, because you get it. The waves are traveling out along the surface of the water in all directions. Okay, and that is how ripples work of water. Okay, will work on the surface of water. All right, so now you understand that is a stationary source. So this source of waves is not moving. Now, the Doppler effect doesn't work for objects that are stationary. You don't notice any shifting of frequency, okay, for just a stationary source like this. Okay, so if you're an observer standing here, you will just hear whatever the frequency is coming from that source of sound waves. Okay, so if this is some object flying through the air making sound, like a siren driving by, you know, whatever it is, you won't hear any shift unless it's moving. If it's sitting still, like a car in the parking lot, and sounding its horn, you will not hear a shifting of frequency. It has to be moving, right? All right, well, let's make it move. So watch. This time I'm going to show you the animation first. So if we get things moving, okay, if we get things moving, pardon me, I just lost my focus on the screen for a second here. Okay, when things move, it gets interesting. So check it out. Our moving dot is moving across the surface of the water like this, right? So here he goes, moving his way across. I'm trying to trace it. It's repeating animation. So here he is moving across. And as he goes, he's making circular waves. So all the waves you're seeing are still circular, except look what's happening in front of it. In front of it, the waves are bunched up, which means they're closer together and have a shorter wavelength. Okay? And behind the objects, the waves are spread out, and they have, therefore, longer wavelength. So let's go over here to this picture. So here, if I zoom in on this, here, that is a shorter wavelength. Now, we know shorter wavelengths have a higher frequency. Okay? And here in behind, we have, this is your wavelength. That is definitely a longer wavelength, therefore a lower frequency. Okay? And that, in a nutshell, is why the Doppler effect happens. So, if you're a person, let's say this is a car or a siren, a car with a siren driving by. Well, if you're standing right here, when these waves hit your ear, they're closer together and therefore have a higher frequency. So you will hear a higher pitch in front of the object, okay? When the object is approaching you. Or moving, oops, not approaching, approaching okay, you will hear a higher pitch. But here in behind, if they had another guy standing back here, these waves are traveling towards his ear, he will hear a lower pitch. Not a lower pith, a lower pitch. Okay, when the object is moving away from you. Okay, so if it's moving away, you will hear a lower pitch. So why is this happening? Well, it's happening because our source is moving forward. So if I just put a little dot that represents the center of every circle, what we see here is that as the object moves to the right in this case, when it emits its sound, it's emitting it at various points here, new waves at various points. So the circles that are being created, the circular waves, each one has a different center. Okay? So we're shifting the location of the center of all our circles, and that makes the waves bunch up in front. They bunch up and they spread out in behind the object. They spread out here. And that's what causes the Doppler effect. Okay? So if you look at this shows it very beautifully here. So look at this animation. Okay, and I hope it turns out well for you. I'm actually recording this using better software than I normally use, so hopefully it's a smooth animation. But yeah, what's happening is you can see the waves bunching up as the source, as the black dot you see right here, is moving to the right. The waves bunch up in front of it and they spread out in behind it simply because it's moving. And that's why you get the Doppler effect. Okay? Now, if you look at a duck in the water, I actually took this picture. Let me erase this. Okay, so the duck is moving. I'm going to redraw it for you. The duck is moving forward, right, in that direction. Whoops, I meant to put V. So the duck is moving this way. So that's the speed of the object. And it's creating waves in the water. And you see how they're bunched together in front of the duck. While water waves, they show the Doppler effect too. Okay, so that is the Doppler effect for a duck in the water, okay, creating water waves, not sound waves, but water waves. There was a typo here. Ignore this. That was supposed to go on the other side. It was supposed to go here. Lower frequency and longer wavelength. Okay. So anyway, that's how the Doppler effect works. So if the object is traveling less than the speed of the waves, okay, in the water, and the waves are sort of get ahead of it, then you're going to get a shift like this. And most objects that we're used to listening to are traveling at lower than the speed of sound, right? All right, so this is the Doppler effect. This is it. That little picture says it all. Okay, that's why the siren sounds high pitched when it's coming towards you and lower pitched when it's moving away from you. It's all about these shifts in frequency. Okay, so the frequency is shifted higher when moving towards you and lower when moving away. I'm going to highlight those words. Okay, and lower when moving away. Very important. Okay, now this is the principle behind police radar guns, between redshift and blueshift in galaxies, between weather data and ultrasound imaging, car horn sounds, fast moving cars, and so on. Now, by the way, what's the deal with redshift? Well, red light has a, here, notice red light has this frequency here, so it has a lower F and therefore longer wavelengths compared to, on the other side of the spectrum, our violet side or our blue side here. This has a higher frequency. Like, look at the frequency, it's 7 times 10 to the 14, where the other one is only 4 times 10 to the 14. So a higher frequency and shorter wavelength. Okay, so if something's moving away from you and emitting light, the light will be red shifted. So in other words, the frequency and the amplitude, or sorry, the wavelength will increase and become a longer wavelength, and I have a lower frequency. So that's red shifted if it's moving away. Okay, but on the other side of the spectrum, blue shift, okay, if it's moving towards you. And there are some objects out there that do move towards us, but generally speaking, other galaxies are moving away from us. They're all redshifted, pretty much 100%. That's how we know the universe is expanding, one of the reasons. All right then, so now we've taken care of understanding the Doppler effect. What if we speed up the object even more though? So now the object is matching the speed of the waves themselves. Well, when that happens, watch. Okay, so now the object is traveling at the same speed as the waves themselves. So take a look at this. Now the object is moving along with the waves perfectly right at the front there. And that creates, instead of the waves being spread out in front, they overlap to create an area of constructive interference. Okay, it's basically a super crest, or if you like, a super compression of air. So here you get constructive interference because the waves actually overlap. They're so close together now, they overlap. Okay, and here's our source moving at the same speed as the waves themselves. And if you were standing right here and this were to hit your ear, this wave front right here, it doesn't sound like a bunch of different frequencies. It's one boom. Okay? You'll hear a boom in your ear, and that boom we call a sonic boom. So when something is traveling at the speed of the waves, you get this shock wave that's created just in front of the object, or right next to the object, called a sonic boom. Now here behind the object, you'll still hear the lower pitch. You'll still hear a low-pitched frequency when the object moves away from you. But in front of it, you won't hear a higher pitch. This time you'll just hear a bang. And you'll hear the bang just as the object's passing you. Okay, and that bang is a sonic boom. Now here's a bullet. It looks reminiscent of a boat in the water, but the boat in the water has the same type of wave effect, same type of Doppler shifting. Water waves move incredibly slow through the water. Boats can easily beat the speed of the water waves, and so they produce this kind of wake behind them all the time. But this is actually a bullet traveling through the air. And here you can see the shock wave. It's only very small because it's a bullet, and you probably won't hear it, okay, unless the bullet whizzes past your ear, and that'd be very dangerous. But yes, okay, that is bullets going at the speed of sound will definitely have a shockwave like that, okay? Now let's go faster than the speed of sound. Well, now here's the object moving faster than the sound it's creating, so all the sound is behind it. And now it's clear sailing, easy to fly through this because you don't get all this turbulent air around the aircraft, and it cuts through the air nicely, but you still get here and here a shock wave of constructive interference, and that will still sound like a sonic boom. Okay, and let me show you an animation. Oh, maybe I don't have an animation. Oh, yes, I do. Okay, let's try this. I should have an animation because that would make sense. Yes. Okay, so let me switch to this view. Let's zoom in a little. So here's the object, and notice how the object stays ahead of the waves it's creating. Okay, and then the sound, the cone of sound forms behind it with a shock wave along the edges of the cone. And that is the sonic boom you will hear, okay, if you were standing right here, for example, as this wavefront crosses your ear, you will definitely hear a shock wave. But if you're standing back here, you'll just hear the rumble of the engines. You will not hear any shock waves behind the plane. But they're right on the edge of that cone of interference, okay? So that's it. That's the Doppler effect. Here you can see a picture of the plane just getting ahead of the shock wave it's creating. And so you can actually see the shock wave here. Why can we see it? Because we don't normally see sound waves. We can see it because sometimes when you compress the air enough, if it's humid air, it will make the water droplets in the air condense and form a cloud. And so you'll see sometimes objects breaking the sound barrier, creating a small cloud, okay, behind them, and you just see this cloud appear just as they break the sound barrier, creating the sonic boom. All right, I wanted to show you this also. This is weather radar. So I'm making this video on Thursday night, and on Thursday night, the forecast for tomorrow is snow. And you can see here, this is not an animated image, but it's a still image. And here you can see snow. And guess what? It's coming our way like that. So we'll get some snow tomorrow. I don't think they're thinking more than 5 to 10 centimeters, somewhere in that neighborhood, but that's significant. Not enough for a snow day or anything, but enough that we'll have to get out the shovels and shovel that thing. And after that, it's going to turn cold again. So welcome back to the winter, okay? Good for the outdoor rink, I guess, so it's on the bright side. But how do they make this radar image? Well, this is using Doppler as well. So this is the Doppler effect, okay, for radar weather satellites. And what they do, the satellite hits the atmosphere with microwave waves, and then the reflected waves back to the satellite get Doppler shifted by any vertical motion in the atmosphere, like when it's raining, okay? And so, and the heavier it's raining, the more significant the effect, and they can actually tell you where it's raining, where it's snowing, okay, and where the storm fronts are based on this technology. All right, so there is a Doppler equation. Now, we never did this in the space unit, so hang on to your hats. Here comes an equation for you. Now, it's a pretty straightforward equation. It's a little tricky to manipulate it, but I'm going to make your life, I'm trying to make your life as easy as I can. So we do all the fun stuff, and you don't have to do too much hard work. But anyway, if you look at this, this is the Doppler equation. So FOBS here, FOBS is the frequency observed. So you're the listener, you're listening to the siren going by. You're the observer. So FOBS is the frequency observed. I should write that down somewhere. So let me write it up here. FOBS is the frequency observed, okay, by the external observer listening to the sound, okay. F source means the frequency of the source. So let's say the siren has a certain frequency. Well, it has many frequencies, but let's say it has a certain frequency. You know, it's a bang, bong, bang, bong. So maybe the top one bang, has a certain frequency. Okay, so we call that the frequency of the source. Okay. Now, let's say the temperature of the air. Let's do an example. Oh, here, wait. So here, I'm getting ahead of myself. Sorry. So here's the equation. I'm going to put it in a box. Now, let's say you have, if you look at this equation, you'll notice that there's the speed of sound in here. Okay, so here's the speed of sound right there. And then it occurs again on the bottom. You can't cancel those out because there's a plus or minus on the bottom. Okay, so the original equation is the frequency observed equals the frequency of source times the speed of sound, and then that is divided by the speed of sound plus or minus the speed of source. And you cannot cancel the speed of sound there. You must leave it in. Now, what does it mean plus or minus? Well, you're either going to use plus or minus. If the object is moving away from you, the distance is getting bigger. We use plus. Okay, and you have to remember that. And then if it's coming towards you, we'll use minus. So the distance is getting less, you use minus. And that's it, because we know there's a difference. When it's coming towards you, the frequency shifts higher. When it's moving away from you, it shifts lower. All right then, let's do an example. Let's say we have the temperature of the air is minus 10. Okay? So then we go ahead and take out our calculator. We find that the speed of sound in air is 326.1 meters per second. So that's using the old formula with temperature, okay, and the number 332 for 0 degrees Celsius. Now let's say you have a car horn or a siren. Let's make it a siren since we did a siren example. And the frequency of the siren is 350 hertz. I'm just making that up, but let's just say it's 350 hertz. Okay? And let's say you are traveling a paltry 40 kilometers per hour, but the police are still around. They don't like you driving at 40, you unsafe, unlicensed children, right? So we take the number 40 and convert it to meters per second. You must do that first, convert to meters per second, by dividing it by 3.6. And we find that 40 kilometers per hour is 11.1 meter per second. Now, if the object is traveling towards you, we're going to use the minus in the formula. And we're asking ourselves, what will that siren sound like if it's traveling towards you at minus 10 degrees Celsius on a cold winter day, driving towards you on the sun, like not right at you, okay? It's going to drive by, so relax. You're not going to get run over. But when it's driving towards you, we go ahead and use the equation. The frequency observed will equal the frequency of the source, which is 350, okay, times the speed of sound in air divided by the speed of sound minus the speed of source. So I've prepared all the numbers for you. And what we see is that I get the horn itself is supposed to be 350. But see how it's shifted higher in the, once we do the math? You get a higher frequency. It shifts up. Now, what if it's moving away from you? Let's keep everything the same. We'll just make one change. Now it's moving away from you. So now in the formula, we use plus instead of minus. I have all the data already. I have the speed of sound in air. Okay, it's 326.1 is the speed of sound. I have the speed of the object is, the frequency of the source is 350, and the speed of the object is 11.1 meters per second. So I put all that in, and now I get a different frequency, this time lower, but that makes sense to us. Okay, this lower frequency, because lower frequencies, when they're moving away from you, like bam, bom, bam, bom, bam, bom, bam, bom, shifting down, right? As it moves away. So it should be lower. And that's it. So there you go, guys. That's a Doppler effect. That's all I can say about it. So let's look at the homework. I do have a worksheet for you this time. Okay, now it's only a few questions, so chillax, Andrew. It's not very much. And I know Andrew doesn't want the March break, so you know what? I admire the spirit there. Don't worry, guys. If we don't have a March break, I will make sure it's going to be so awesome at school for you that you will not miss it at all. Okay? Don't worry. You know, the homework will be fun. and the lessons will be amazing, and I'm really going to enjoy seeing you there during your March break. That'll be really funny. I think that that's one for the history books if we cancel the March break. I'm excited, okay? Maybe they will. Anyway, take a look. I have very nicely for you arranged the formula. There's only one formula, by the way, but I have written 4 formula here, and what I've done is I've solved the formula for relevant variables, because this one's a bit tricky to do the algebra. So here, if the object is moving towards you, you can use either this equation, we'll call it number 1, or this equation number 2. Now, this equation if you want the frequency observed, but sometimes we want to know the speed of the source. Let's say a guy drives past you. How fast was he driving, okay, when he drove past you? Well, we can use the Doppler equation to tell. So this is if they're going towards you. Now I'm going to put a little line down the middle. If the object, on the other hand, is moving away from you, well then notice how the equations slightly change. We have plus down here, and this has changed also, okay? So that's it. There's all your equations. Now, let's go ahead and look at the questions. It says, in all examples, the air temperature is 10 degrees Celsius. So let's once find the speed of sound. So speed of sound at this temperature would be 332 plus 0.59 times t. Okay, well that is 332 plus 0.59 times 10. So that's 332 plus 5.9, that's 337.9. Look at my genius math skills. I didn't even use my calculator for that. Did you use your calculator? I know you would. Okay, I know you would. So 337.9 meters per second. Very good. All right, so let's look at question number 1. A car is traveling at 30 meters per second and sounds its horn at 250 hertz. What will you hear? What frequency will you hear, okay, if the car is moving towards you? So the frequency that you hear is FOBS, right? The frequency observed. Oops, I'm sorry. I'm making mistakes with the keyboard. Frequency observed, like that. Okay, so that's what they want. What frequency will you hear? The frequency observed. So I go back to my equation. If they're coming towards me, okay, I'm going to use this equation here, the frequency observed. Okay, so let me write it in the margin. The frequency observed equals the frequency of, the frequency of the source times the speed of sound. And then that's all divided by the speed of sound. Is it going towards them? So it's minus the speed of source. Okay? So now all I have to do is plug in all the numbers, right? So the speed of sound I got at the top was 337.9 in all of these questions. So it's going to be 337.9. And the frequency of the source is 250. So I'm going to write 250 times 337.9 divided by 337.9 minus the speed of the source, and the speed of the source is 30. Says in the question. 30! There you go. All right. Taking out my calculator, I must evaluate what's on the bottom first. The way it's written like this, it's like it's in brackets. So I'm going to take out my calculator. 337.9 minus 30 is easy. That's just going to equal 250 times 337.9 on top. But then that's going to be divided by 307.9 on the bottom. So now I take out my calculator. Go 250 times 337.9. I did too many decimals. 337.9. Okay, and then I'm going to divide that by 307.9. And then I press equals. And I get 274 hertz. So 274 hertz. So it's shifted higher. The horn is actually 250, right? But it's shifted higher because it's coming towards you. Now I'm going to let you do the rest of these. Okay, notice I did get the right answer, obviously. Obviously, it's me. Gotta get the right answer, okay? So, anyway, how about you? Can you do the second one? If we'll make one change, now it's moving away from you. Well, if it's moving away from you, all you have to do is change that minus to a plus that's in the formula. Or just come up here, use the chart, and you'll notice you use this one. You'll see you get a different answer. This time it'll be shifted higher, not lower. Okay, and that's it. So let me now show you the homework I would like you to do. There are a few questions here, just a few. 1, 2, 3, right? 3 questions, but there's A, B, so you know, whatever, a few questions there. 5 questions, whatever. Not a big deal. But then the textbook contains homework as well. So we did just one lesson, lesson 7. So now we are at lesson 7. And there are a few questions in the homework here I would like you to answer as well. Now, we have a test on Monday. Don't forget, the test is only up to lesson 5. It's more like a quiz, but you know, I don't know. If I say it's a quiz and there are 10 questions there, you know, or whatever, you're going to get mad. So I'm just saying it's a test, and then if it's shorter than you might imagine, you'll feel happy about that, right? But if it's longer than you think, and I say it's a quiz, then you're upset with me. So I'll say it's a test, and I'll err on telling you that it's long. Okay? Yeah, but there's not really a whole lot to test there. Everything up to and including resonance and strings. Okay, and that's it. Now, this other homework, please make sure you have it done. You know, you've got now the weekend and everything. I'm not going to check this before the test. So, you know, on the day of the test on Monday, there will be a lesson after the test, and that lesson will be quite short. We'll do lesson 8 after the test, which is beats, echolocation, and sonar. Okay, and that is a very short lesson, and then you can do that homework, whatever, afterwards. I think you'll probably get most of that done in class because the lesson is quite short. So anyway, that's it for now. And we're working our way through, right? Doing a lesson a day. I'm trying to go a little slower for you so that you can just focus on one thing at a time for us. And that's it. All right, so I'm going to stop the lesson here. I will see you on Monday. Okay, so have a good weekend. Enjoy the snowfall, and then enjoy the cold after that. And we will talk again soon. So have a good weekend. Oh, and don't forget, Ada, please practice your badminton. Okay, yeah, needs a little work. But Robyn, really good. Okay, really good. All right, have a good weekend, guys. Talk to you soon.